density is defined as mass of air per unit volume. Therefore, the density of the atmosphere at any given place may be defined as the mass of air contained in any given unit of volume. In other words, how much air is inside a given space. Density can be expressed in many ways. One way is by using grams of air per cubic meter, or in standard international units, kilograms of air per cubic meter. You may recall from the lesson on the atmosphere that we talked about the ICAO Standard Atmosphere, or ISA. At sea level, ISA states that the density is 1,225 grams of air per cubic meter. So we have a mass which is 1,225 grams in a volume which is 1 cubic meter. However, there are other ways in which density can be expressed. For instance, if we know the standard sea level density in ISA, then we can use this as a benchmark to compare densities from other areas. Using this method, we may take the density of 1,225 grams per cubic meter as representing 100%. If in a given place or at a given altitude the actual density was only 1,000 grams per cubic meter, then this density would be approximately 82% of the ISA sea level density. We call this expression of density relative density. We are comparing the prevailing density to the density at sea level according to ISA. Another way density can be expressed is by using the term density altitude. This term is seldom understood, but it is essential to understand it, especially when using it to discuss aircraft performance. Density altitude is simply defined as being the altitude in ISA at which the prevailing density would occur. This is best explained by using an example. Let us say we are at sea level, and the atmosphere happens to be exactly the same as standard. The density at sea level in the real atmosphere will therefore correspond exactly to that found at 0 feet in ISA. However, if the density at sea level in the real atmosphere falls to 1,000 grams per cubic meter, this new lower density at our location will correspond to a density found at a higher altitude in ISA. In our example, we can see that the density at sea level in the real atmosphere equates to a density found at 10,000 feet in ISA. We therefore say that the density altitude at mean sea level in the real atmosphere on this particular day is 10,000 feet. The knowledge of density altitude is important in assessing the effect of the changing density on aircraft performance. We will cover this later, but now let us see how we can actually calculate our density altitude. There are two simple ways of calculating the density altitude. One method is by using a flight navigational computer, and the other is by using a simple numerical formula. This formula states that for every 1 degree Celsius away from ISA, depending on whether the deviation from ISA is positive or negative, you add or subtract 118.8 feet to your pressure altitude to find your density altitude. Let us look at an example. Let us say the pressure altitude is 2,000 feet and the temperature is 25 degrees Celsius. This means the atmosphere is 14 degrees warmer than ISA. Therefore, the ISA deviation is plus 14 degrees Celsius. We now see that the density altitude is 3,663 feet. Having seen the various ways of expressing density, let's have a look at what controls atmospheric density. Looking at the diagram, we can see the density formula. Notice that in the formula we replace the word density with the Greek symbol rho. We will now look at how the variables of temperature and pressure affect the mass or volume, and therefore the density. Let's first look at how pressure can cause see a mass within a volume. As we increase the pressure surrounding the parcel of air, you can see that it gets compressed. This causes the density to increase. Conversely, if we reduce the surrounding pressure, the parcel will expand and the density will reduce. Physical experiments confirm that density is directly proportional to pressure. The other main variable that controls density is temperature. Looking at the diagram, we can see that as we heat a parcel of air, the particles get excited and cause the parcel to expand. This reduces the density. Conversely, if we cool the parcel of air down, it will shrink, and the density will increase. Therefore, density is inversely proportional to temperature. Having seen the effect of varying temperature and pressure on density, let us now consider the effect of altitude on density. Here we have a conundrum. As altitude increases, temperature falls. Therefore, density should increase. But as altitude increases, pressure also falls. This causes the density to decrease. So what does happen to density with altitude? The predominant effect is the change of pressure. The reduction in pressure reduces the density more than the reducing temperature causes density to increase. Since pressure is the dominant factor affecting density, it follows that because pressure decreases at a decreasing rate with altitude, so will density. Looking at the diagram of ISA, we can see that relative density decreases with altitude at a decreasing rate. There is one more variable that can alter the density of air. This variable is water vapour. This effect is complicated and beyond the scope of the expected level of knowledge needed for the private pilot. It is sufficient to know that the density of the gas water vapour is less than the typical density of the gases composed in a sample of dry air. Therefore, the greater the humidity, the lower the density. We have so far seen that high altitude, high temperature and high humidity environments all decrease air density. A knowledge of atmospheric density is vital in understanding the effect density has on aircraft performance. Lift is directly proportional to density. Therefore, a reduction in density will cause a reduction in lift. This is a performance-reducing characteristic. But density affects piston engine performance as well. The lower the density, the lower the amount of oxygen that will be in a given volume of air. This oxygen is essential to combustion. Therefore, a reduction in density will cause a reduction in engine performance. The combined effect on engine and airframe efficiency of a reduced density needs to be accounted for. Most density changes are accounted for in performance graphs by the use of altitude and temperature nets as shown here. The example shown is the landing distance graph for a small single-engine aircraft. This completes the lesson on density. Be very careful not to exceed the limitations of the aircraft and accurately account for density using the altitude and temperature corrections in the aircraft manual.